and long transmission line. Okay, so then after that, nothing but we have seen what is the effect of our corona effect, then Ferrantic effect we have discussed, then how to calculate the sag and tension in our transmission line, how to calculate the sag and tension in our transmission line. Okay, so these things we have discussed and we have solved some of the numerical problems related with those things. Okay, so today in the first half, in the today's session, first half we will see that the important topic is going to be of the next important topic is going to be of the type of towers. Remember the type of towers you can call as often line support. Then we'll move to the next part. We'll solve some additional problems on the previous topic whatever we have seen in the calculation of sag and tension and about the long transmission line and corona. We'll solve some of the problems, numerical problems on those things, on those topics. Okay, so today we are going to start with the another important topic that is going to be of the tower. The tower you can also call it as your line support. The tower or nothing but you can call it as your line support. So the main supporting unit, it means the main supporting unit of our overhead transmission line conductor is nothing but we are calling it your transmission tower or nothing that is going to call it as your line support. Okay, so this but we are using of different type of structures. Either maybe of the polar towers will be used for our transmission line or transmission line to carry the conductor, right? So that type of structures only is going to here is going to call us of your line support. That type of structure only here is going to call us of your line support. It means the transmission tower have to carry the heavy transmission conductor at sufficient safe height from the ground. Okay, it means there should be the line support should play the major role in our power transmission. Why? Because that only has to carry the conductor. Okay, and apart from that, there should be a proper spacing between the conductors, and that and the from the ground also. Right, between the conductor also there should be often sufficient space should be there, and the ground clearance sufficient ground clearance should be there, so that it should be maintained. Otherwise, nothing but there will be of nothing but interference will be there, and this clearance in how it's decided, it will be decided on the electrical and mechanical consideration, both the things. In the previous session, we have seen what is the sag and what is about the ground clearance and what about the tension, all those things. So those things is going to be often applied in the while erecting the towers. So when designing a structure or the tower, right? So what property it should have? Right? So the line support, it should have often high mechanical strength. Because it should have often high mechanical strength to withstand the weight of the conductor and the wind loads. Because the tension will be there. That tension has to be carried by the towers only. Okay, and apart from that, we cannot invest a huge amount for the erecting of the towers or the line support. So it should be light in weight without the loss of our mechanical strength. Because in the starting of the introduction class of the transmission distribution, we seen about the economics of generation. So the cost, okay, the cost, in that cost we have seen about what is the fixed cost. The fixed cost means the initial investment for the generation and initial investment for the transmission and distribution. So it means the ROW, right of way. It means where the conductor and the transmission lines are going to be often placed, that we are calling often right of way. So it means the cost we have to invest the cost for the transmission and distribution also. So suppose I am placing the tower in the private land, then I have to pay the compensation for that one, right? It means I am going to give the right of way cost, right? So that is going to be often comes in the picture also. Okay, so that's why when you're making of your tower, that the size of the tower and the strength of this tower is based on the conductors and the transmission capacity. See to that nothing but the tower when it's going to be erected, it should be cheap in cost and economical to maintain. And it should have the life should be of your longer life. Okay, and the tower should have of an easy accessibility of the conductor for maintenance. Okay, so what are the important parts will be there in your transmission towers? Have you any idea? Okay, we'll see that what are the important parts will be there in our transmission tower. So we will have the cross arm, you will have the boom, you will have the cage, and you will have the tower body, legs, and you have the stubs. Like this, we'll have the various parts in our transmission towers. Okay, so on what basis these towers are going to be often classified? On what basis these towers are going to be often classified? Okay, so as I told nothing but the main requirement of the line support is nothing but the low cost, low maintenance, expensive, and long life. So based on that, nothing but the towers are going to be often classified into two types. One is going to be of an electric pole, or you can call it as often electrical tower. Okay, so electrical pole on electrical tower, and we'll have the sub classification on both the types of electrical pole and electrical towers. Okay, so what the difference between the electrical pole and electrical tower, right? So when a pole is with the support for often smaller voltage, it means the voltage lesser than 115 kilovolt transmission line. So then that type of Nimbert pole is going to call as of your, or support is going to call as of your electric pole, right? So normally this electric pole will use it for the voltage less than 115 kilovolt, less than 115 kilovolt. So such type of Nimbert is going to our type of support is going to call as of your electric pole, and that electric pole usually is made up of wood, concrete, or steel. It means the concrete means reinforced steel Nimbert concrete, and Nimbert the steel towers, or maybe a fair steel tower. So we'll use only these three type of Nimbert pole only we'll using for the electric pole. Either maybe of your wood or concrete or steel. So will be of labor. So a pole which is supporting for the smaller voltage transmission system. So then that type of pole here is going to be called as of your electric pole. Then that is going to be called as of your electric pole. Okay, what when your voltage, remember the tower erection here, remember that is going to be carrying often high voltages, right? More than 150 volt, or maybe if you're 230 kilovolt and about 230 above kilovolt, only we need only the structure of your towers only. Okay, so nothing but normally that structures will be made up of your aluminum or steel, which gives the strength for supporting the heavy electrical conductors. Supporting the heavy electrical conductors. Okay, that we are calling your towers. So the line support here is going to be often classified under two different types. One is going to be of an electric pole, another one is going to be of your electric tower. Okay, the pole means something, but normally we'll use for the lesser voltage transmission system and distribution system. We'll use the lesser voltage. There we'll use of an electric pole. Okay, so electrical tower, but when the voltage is going to be of greater than 115 kilovolt, or maybe of but compulsory about 230 voltage, we'll use only the towers. So that towers will be made up of aluminum or steel. Aluminum or steel. Okay, so here nothing but the type of towers here in the but that categorized based on the voltage, and but will have of an A type, B type, C type, and D type. It means that remember the angle of deviation based on the angle of deviation. Suppose if the angle of deviation is going to be upon 0 to 12 degree, then there is going to be of called as your A type. If your angle of deviation is going to be upon 2 to 15 degree, then there is going to be called as your B type. 15 to 30 degree means that is going to be called as of your C type, and D type means remember 30 degree to of your 60 degree, that is going to be called as of your D type of towers. The towers remember is going to remember. So here how the towers are going to be made, but that is how much amount of force will be applied on the conductor. So the cross arm based on the cross arms. Right, so that based on that only that is going to be often categorized. That may be a further to be classified as often tangent suspension tower or angle tower, or maybe that you can call as often tension or section type. Okay, so apart from these two type of towers, we'll have often special type of towers also we are having. We are having often special type of towers also we are having. So like when the river crossing, when there is a river crossing, we'll use often river crossing type of towers. Okay, when we are using for the railway or highway crossing, there we use often separate type of railway crossing towers, or nothing but exclusively one special type of towers we'll use often transmission towers. Okay, so this is the number. Based on the number, the application wise we can also classify as often river crossing tower, or maybe of your railway towers, or it may be of your transmission towers. Okay, so but how many type of conductors we are using, the circuits? how many type of circuits we are using. Okay, so based on that also we are classifying that one is going to be of a single circuit tower, or double circuit tower, or multi circuit towers. Multi circuit towers. So we'll see what each and every type individually. Okay, so and it comes with respect of your electric pole. When it comes with respect of your electric pole, I told you nothing, but we'll use often three types of poles we'll be using. So one is going to be of your wood poles, second is going to be of your concrete poles, and third is going to be of your steel poles. The first diagram, this diagram, which will be delivered with shows of your typical wood pole construction. This is going to be of your typical wood type of constructions. Okay, so this is going to be a fair wood type of constructions. We'll use this wood. So normally this type of construction of towers will use it for your low voltage transmission and distribution network. Okay, so but next, but this is going to be of source your concrete poles. This is going to be of your concrete. It reinforced steel, but concrete poles. Okay, we'll use this type of towers for your electric pole. Okay, or this may be of your steel towers. We'll use this type of your steel towers. So this is going to be of your steel poles. So this is going to be of your steel poles. Okay, so we'll see each and every one category. So normally when it comes with respect of your wood poles, so it's a cheapest number, depends upon the availability of the wood, right? So we'll make it as of the number the supports. So normally this will be used for often span of short span with having of tension of low tension. Okay, so normally the wood poles will have the limitation of the height and the diameter. Higher the height, nothing but we cannot able to use the wood. Okay, so here remember, these wood pole structures may be often formed as often A type or H type. Okay, so for why we are using often A type of structure or H type of structure means to have often greater strength. Okay, to have of a greater strength. Okay, so normally this going the can either maybe a fair 2 or 4 times the strength of your single pole. So that's why we are using of a A type or H type, right? So H type normally will be employed for your 4 terminal poles, right, which carrying the switch gear as well as of your transformer. So there will use of your H type of constructions for employing of the conductors or maybe of your transformers. Okay, so this is the diagram which shows how about your wood pole. Okay, so this will be the first diagram which shows about this is the first diagram which shows about your air type of constructions of your wood, air type of construction of your wood. So this is nothing but where we are placing the insulators on your cross arm. Okay, these are they are going to be called as a cross arm. Okay, so this is a pole which we are making down. So here nothing but so normally here but the main objection here the wooden support we cannot able to draw it on the ground level. Okay, so comparatively the life will becomes for 20 to 25 years. We cannot use for the voltage more than 20 kilovolt. We cannot able to use it because the conductors and the diameter is going to be often higher. So it will have the less mechanical strength. Okay, so normal periodical inspection is going to be often needed for this type of wood type of faults. Okay, so here nothing but we'll use this type of H type we'll use for the but and normally when you have the switch gear and as well as of the transformer with the conductors, then we'll use of this type of steel number H type. Okay, so with steel bracing. So non-technical person should not climb that pole. So that's why here we'll have the steel bracings will be there. Okay, to protect the towers. So this is but in the electric pole, this is structures we there will go for often nothing but concrete poles type. Okay, so normally the life will be more than compared of your wood pole. Okay, so but the maintenance cost here is the concrete pole is going to be often less, but that not in the case of your wood pole. Okay, so it will be of nothing but normally but the chances are there to get damage when erection or maybe if you are loading your but structure. It means but when you are loading your transformer or the conductor, there may be of nothing but damage may happen to the poles. When the damage is going to happen to the poles, then the mechanical strength property is going to be often losses. Okay, so then it won't come for often longer life. That is one of the disadvantages one comes with respect to the handling is going to be often nothing but it's going to be often very difficult. Okay, since it's going to be often pre-stressed concrete supports. Okay, it means we have to assemble only at your job site. Okay, so the more durable and comfort of the any other type. Okay, the material used will be often less and durable than the other type of poles. So when it comes with respect of the concrete pole, so these are structured. This is structure normally we use for the concrete pole. Okay, so normally this height will be often nothing but will have often nothing but the breadth will be often 3.35 meter. Okay, and the height will be of nothing but the first insulation height will be normally around 7.5. So it depends upon the voltage. This is normal. This is going to be will use for a low voltage transmission capacity. So compared to that, suppose in case of this is going to be normally 20 kilovolt. This normally will the structures will use it for of normal for often less than 20 kilovolt. If it going greater than 20 kilovolt and but maximum 110 kilovolt or 115 kilovolt, we use this type of concrete structures. We'll use this type of concrete structures. Okay, see here how the span length between has been given for often different and different spaces. Okay, so normally this number the steel poles may be often three types. One may be often rail poles or tubular poles or rolled steel joints or rolled steel joints. So we'll use this type of different type of structures in our concrete poles. Okay, so the total height of the tower here may be of your 10 meters. Okay, so in this case it will be of your 9 meters. So next type of electric pole structure here is going to be of your steel towers. Okay. So normally here nothing but for longer transmission distance with higher voltages. It means the voltage the transfer at the generation level the voltage will be of your 11 kilovolt. It will be stepped up to often 110 or maybe of your 230 or maybe of your 400 voltage. So up to 110 we'll use often steel towers. Okay, so here remember for long steel towers are in, but invariably we are going to employ it. Okay, why? Because it will have the greater mechanical strength, longer life. It can have many, but at different climatic conditions, it can able to handle. Okay, so and we can use the longer span for but for the erection of your conductors. Okay, so but the broken or maybe a puncture insulation will be but considerably reducing the longer span. So that's why we go for of your longer span. So that we will discuss when we are discussing the next module about your insulators. Okay, so why we need of the cross arm and where to limit the cross arm, how what is the length of the cross arms that we are going to say. So normally here nothing but the steel towers that will be grounded, the tower foot will be grounded by driving the rods into the earth. Okay, the minimum lightning troubles as the tower acts as of your lightning for the conductors. So this number is going to remember this will minimize the lightning troubles as the tower acts as of your lightning conductor. It means so tower will observes your lightning strokes. I think in the first unit we have studied about the first module we have studied about the lightning and lightning arrestor. So when you are placing in the lightning arrestor on the top of the towers, means the lightning will strokes on the tower, it not on your conductor, so that we can avoid the surges on your conductors. So that is one of the main thing when it comes with respect of your steel towers. Okay, so this is nothing but how the steel structures is going to be often nothing but is going to nothing but designed. So normally this is nothing but 110 kilovolt span with up to 230 meter and 320 meter. Okay, see the height of it. For higher voltages, nothing but the tower height is going to be often almost is going to be of here so 20 meter. Okay, so for nothing but for 110 kilovolt it is going to be often nothing but so that first conductor starts with the ground clearance of 12.5 and there will be often 3.5 and for the next number between the conductors and between the tower 2 of the last conductor will have 4.5. Okay, so if you take that total span with the cross arm, the total span with your cross arm will be of 5.75 meters. Okay, so that remember that will be in terms of 11 meter in case of your 220 kilovolt and the span both are the span of the structure span is going to be from 320. Okay, so the total height of the tower it will be of your 41.6 meter will be of your total height of your towers. Okay, this is the structure how we will have of your steel towers. Okay, so this nothing but this tower that this type the tower see here. So if you see here in the one circuit one number this diagram but we'll have only of here number R phase, Y phase, and here we will have a B phase. So this type of structures normally we'll use for often single structure. But single circuit, this will be we are using for often single structure. So see here but we are having often nothing but R Okay, Y, and this is going to be of your B. And similarly here we'll have of your R dash, okay, Y dash, and your B dash. Okay, so this is normally this will be we are using for a fun double circuit configuration tower. This is the structure of your double circuit transmission towers. Okay, so first one will show the picture of your single circuit, and second number 220 kilovolt, which will span up to the 320 meters, which I have shown here is going to happen. So your the direction of how we are going to direct it for your double circuit. Okay, so this hang. So this hang part, which we are calling software insulator, that we are going to study about the what is the insulator, what is the purpose of the insulators, and what are the different type of insulator we are going to study it in the next module. We are going to study in the next module. But when as I told, the line support of the tower, we are having often two broad classification. One is going to be calling of an electric pole. It means when the voltage is going to be less than 110 or 115 kilovolt, then we use of an electric pole. The tower is going to be called as of an electric pole. When your voltage is going to be often higher, we cannot use the electric pole. Then that is going to be called as of your electrical towers. But that is going to be often nothing but either maybe of your self-supporting towers, or it may be of your angle towers. Okay, so self-supporting towers in the inverter will be categorized into often two things. One is going to be of your wide base or narrow base towers. Okay, so but this is going to be called as of your lattice. But Chris Crown. This is going to be called as of your lattice. This is sorry. So this nothing but this crisscross. So this crisscross. So this is going to be called as of your lattice cross. Okay, so this nothing but. See here in the wide base of tower, the lattice crisscross with the roster connection is adapted. Okay, so each leg has often separate foundation. We'll use often each leg for often separate foundation. Okay, so in the narrow base design, we'll use often lattice, and the construction of angle, channel, and the tubular steel section will be bolted or welted connections. Okay, so then here only we'll use of a tangent tower. Okay, it means that straight run of line. If you see, means the conductor will be often running straightly. Okay, so there we'll use only the suspension insulators. Where we'll use only the suspension insulator. But suppose where we are having the curvature, or we need to change the direction. Or you can how to take the curve on this, that will use will use often deviation tower. Okay, that will call us often line changes, that we are calling often line changing direction towers. That we will calling often line changing direction towers. This normally will be of your self-supporting towers. This will call us of your self-supporting towers. So depends upon the self-supporting towers and direction, this insulator configurations will be often get changes. Okay. And the second category in our steel towers, the towers means will have often guided or stayed towers. Will have often guided or stayed towers. It means the stay wire will be there. Will have often stay wire will be there. So, to give the additional mechanical supports to the towers, right? When there is often heavy conductors are going to be often pressed, the tower won't collapse, and it will be often nothing but guide. It means a state. Okay, so this type of structures we'll use for normally we'll be using for the but either maybe a weed type or maybe a portal type of gate towers we'll be using. So we'll have see here there is a question about how. So the tip top this going to be will have a lightning arresters. We'll have of your lightning arrestor. This tip top is going to be a lightning arrestor. The ground conductors will be often moving. Okay. So the tower here, when it comes with respect of the tower, means the main supporting unit of our overall transmission line is the we're calling software transmission tower or line support. That is going to be called a software line support. Okay, so this is going to be of nothing but it is need of a higher mechanical strength and cost should be of less, and it should have often less maintenance cost, and durability should be often higher. So these are main important properties of the requirement for the towers. Okay, so they're based on the voltage and the distance. The tower is going to be often classified as of an electric pole or electrical towers. When it comes to respect of an electrical pole means a will use of an wood or concrete or steel. Okay, so when it comes with respect of a but towers, electrical towers, will use of an angle towers or will use of a tangential suspension tower. Right? In but we are calling this often self-supported towers. That is going to be called as of a self-supported towers. Okay, so that may be of your tangent suspension tower or maybe called as of your angle tower or tension tower or section tower. Okay, so apart from that, we are having a special type of towers, nothing but for the river crossing towers. We are having crossing the transmission whenever it's crossing the river, we'll use of on river crossing towers, or in the railway crossing, we'll use of on railway crossing towers or highways. Okay, and we'll have these river transmission towers. Okay, so apart from that, based on the number of circuits, either maybe of a single circuits or double circuits or multi circuits, the transmission tower also is going to further classify based on the circuits. So, any doubt? Any doubt? Students, do you have any doubts regarding the electrical towers, number types of towers? Okay, Abhirami, no, sir. Srideya. Yes, students, you can, but now we'll move on to the problem. Okay, so we'll move on to the problem. Okay, so just ping to the board and copy the problem, first problem. We'll start solving these problems. Okay, as I told you, but Students, as my voice is audible?
சார் வாய்ஸ் கேக்குது சார்.
Okay, sir. Okay. So first problem what we are going to see in the today's session is going to appear the continuation of the SAG calculation. So I think in the previous session we have covered the problem related with respect of the calculation of SAG and tensor in our transmission. The levels are supported at equal levels. What will be the SAG? What about the SAG? Right? When the levels are unequal, supported with unequal supports, what about the SAG? So how to calculate? You have seen the previous having and of wind pressure and how to calculate the vertical sag. The problem the presentation I am technically has a span of 150 meters wind level. The conductor has a cross-section area and has a cross-section
வாய்ஸ் பிரேக் ஆகுது சார்.
சார்
தமிழ் சார்,
சார்
வாய்ஸ் இப்ப பிரேக் ஆகுது சார். இந்த ஒரு ஆமாமா ஒரு 30 செகண்ட்ல பேசுனீங்களா, அது வந்து பிரேக் ஆகுது சார்.
ஓகே. Sir, now
சார் சார் இப்ப சுத்தமா கேட்கல சார். சார் வாய்ஸ் சுத்தமா கேட்கல சார். தமிழ் சார், வாய்ஸ் சுத்தமா கேட்கல சார்.
having of where the conductor here is going to having of your means the weight of the conductor is going to be of nothing but not only the conductor weight, you will have it means the total weight on the conductor is going to be conductor weight of your the of the external wind pressure will be there, additional so that is going to called as of your wind pressure WW. Okay. So I have to calculate here what is the level here. For calculating the width of the conductor, given what is the specific gravity of the I'm going to the conductor using the specific gravity and the volume. They give the wind pressure 1.5 kg, 1.5 kg. The given the span length. The span length is going to appear 150 meters. The span length is going to appear 150 meters. Okay, and see they given of the river 200 kg. So tension they given that is 200. Specific gravity they given what is about your specific and conductor in the wind pressure. Sir? Sir, voice? ஆமாம்மா நாய்ஸே வருதா? சரி சார், நான் ஒரு நிமிஷம் கட் பண்ணிட்டு மாட்டி உள்ளே வரேன் சார் லைனில்.
Sir, now voice is audible, sir.
சார் இப்ப கேக்குதுங்க சார். நீங்க கண்டினியூஸா பேசுங்க, எப்படி கேக்குன்னு பார்ப்போம்.
Hello, sir.
சார் இப்போ நீங்க பேசுனது கேட்டுச்சுங்க சார், தெளிவா கேட்டுச்சு. ஆனா நீங்க அந்த கண்டினியூஸா பேசுறப்ப எப்படி இருக்குன்னு தெரியல சார். ஒரு சென்டென்ஸா சொல்லுங்க சார், பாத்துருவோம் கரெக்டா வாய்ஸ் வந்துருச்சான்னு.
So now voice is audible?
சார் இப்போ சிங்கிள் வேர்டா பேசுறப்ப தெளிவா இருக்கு சார். இது கண்டினியூஸா நீங்க 4 வார்த்தை பேசுறப்ப பிரேக் ஆகுது சார்.
Okay, okay, sir. Okay, now slower. Cross section area, 2 specific gravity, 9. Okay. So for calculating weight of the conductor, I have to calculate what is the weight of the conductor. Okay, weight of the conductor. But it is equal to per meter length. It means specific gravity into per meter. So specific gravity is given 9.9. So the specific gravity is going to be of 9.9. Section area 2 into multiply this one, you will get 1.98. So you will get the weight. You have the conductor you will have of your ice coating. You will have of your ice coating. Okay, along with that, I will have my wind pressure. Wind pressure. So this is the total weight. Total. I have to calculate the total weight of the conductor. I have to calculate what is the total weight of the conductor. So total weight per meter. So nothing but it is going to be total weight is going to be square root of, okay, double is going to be the weight of the conductor, nothing but wind pressure W square plus W of W wind pressure square. Square root of 1.98 square plus 1 1.5 square. So you get the value of kg. Okay. We know what is the formula for our sag. We know what is the formula of L square by 80. So that is sag formula. Weight that is going to appear WT L square by 80 means the total ice coating plus the wind pressure. Total weight. Total weight 2.48. So it is wind pressure 2.48. Okay. Pressure 150. So that is wind pressure 150 meter square by 8 into T. Given the tension the conductor is going to appear 200. So into 200, you will get the value. What is the value of your sag? Come on, the value of your sag value. What is the value? What value got it? So you will get the sag is going to appear 3.48 meter. You get 3.48 meter sag. Vertical. So vertical we are calling sag plant sag. That is plant sag. Nothing but that is S is equal to vertical sag by cos theta. Right? But if you want to have a fun theta means you have to calculate your tan theta. So tan theta here. I draw this one. Pressure. So the pressure is going to be 1.5. So 1.8. This value is here 0.7. It means theta will be equal to tan inverse of 0.7. Theta is equal to tan inverse of 0.7. So it means my theta value will be equal to 37 degree 48 minutes. 12.8 equal to, okay. Of 1.1. So you got it? Gravity and the weight of for calculating the theta, that is going to be the resultant weight. This we are using the what about your vertical side? So this is nothing but when the conductors are at normal, is not at normal. It means the weight of the conductor is not the actual weight of the conductor. It will have an actual weight of shaft. Okay. So we'll move to the next type of column. That is nothing but okay. There and we are seeing what is the formula for a visual voltage and critical visual voltage. That we are going to use it directly to calculate what about your corona.
சார் தமிழ் சார் இப்போ வாய்ஸ் அதிகமா பிரேக் ஆகுது சார். இடையில கொஞ்சம் பரவாயில்லாம இருந்தது சார். இப்போ வாய்ஸ் திருப்பியும் பிரேக் ஆகுது சார்.
சார்
வாய்ஸ் ஃபுல்லா பிரேக் ஆகுது சார்.
சார் நான் சிஸ்டம் ரீஸ்டார்ட் பண்ணிட்டேன் சார் இன்னைக்கு சார்.
ஓகே சார்.
சிஸ்டம் ரீஸ்டார்ட் பண்ணிட்டேன்.
ஓகே சார், ஓகே சார்.
நீங்க கனெக்ஷன் நார்மலா தான் காட்டுது சார் இதுல.
ஓகே சார், ஓகே சார். இப்போ அந்த ஒவ்வொரு வார்த்தை பேசுறப்ப தெளிவா இருக்கு சார். அந்த போர்ட்ல இருந்து பேசினாதான் இந்த இதா வரல.
ஓகே, அப்ப ப்ளூடூத் ஒரு இதா இருக்கும்.
அதான் சார், அதான் சார்.
டெஸ்ட் சிக்னல் கரெக்டா தான் காட்டுது இதுல.
ஓகே சார், ஓகே சார். அதான் இப்போ வந்து நல்லா தெளிவா இருக்கு சார். நல்ல கிளாரிட்டியோட இருக்கு. அதே போர்ட் சைடுல போயிட்டு இது பண்றப்பதான் இந்த ஒரு 4 வார்த்தை சேர்ந்து வர்றப்ப இந்த பிரேக் ஆகி வருது.
எழுதிட்டு இங்க வந்து கொஞ்சம் எக்ஸ்பிளைன் பண்ணிட்டு அங்க போறேன் சார்.
சரி சார்.
தட் ஐ வில் டு.
ஓகே சார்.
phase conductors of 2 centimeter diameter. So here they given a three-phase line has a conductor of 2 centimeter in diameter. Conductors of 2 centimeter in diameter, phased equilaterally 1 meter apart. Phased equilaterally 1 meter apart. If the dielectric strength of air is 30 kilovolt per centimeter maximum, right? Find the critical disruptive voltage for the line. Disruptive voltage for the line. Assuming that air density factor del is equal to 0.952, irregularity factor m naught is equal to 0.9. M naught equal to 0.9. So here remember we have to calculate the critical disruptive voltage. Okay, so directly we are going to substitute in the formula. When we have seen about the corona, what is the corona and what is the critical disruptive voltage and critical visual disruptive voltage we have seen. So I think I have given the two formula there. So by using the voltage gradient formula, so you have to use that formula directly to substitute to get that value. Okay, so here you have need to remember this formula to find out the voltage. Okay, you need to find, but remember this formula. It means both the formula is going to be very important. One is going to be critical disruptive voltage, another one is going to be critical visual disruptive voltage. So that formula you have to remember to calculate the values of your voltage, critical voltage. Okay, so I'll write. So voltage that is going to call the software VD. Disruptive voltage VD. The VD formula is here nothing but M naught or del G naught ln of D by R. Ln of D by R. So here you see the M naught given and they given. Okay, G naught is given respect of here dial resistance that given the diameter, you have to calculate what is the voltage radius. R will be equal to D by 2. So D is given diameter is going to be 2 centimeter. 2 centimeter by 2, that is going to be 1 centimeter. This is my R value. This is my R value. Okay. Here I need to calculate my G naught. That should be of your RMS value. But it is maximum. Maximum value by root 2 is going to have here. Maximum value by root 2 is going to have here RMS value. Okay, right? So that is G naught max by root 2. It means 30 by root 2. So you will get 1.21 volts per centimeter. Just substitute those things in the disruptive voltage. Just substitute all those things. Substitute your M naught or okay. Z naught we have calculated. Delta, you know that you can get your values. We're getting 12 point. Someone has posted the answer. Abhirami, 12.5. I think somewhere you made a mistake. Check it out. So VD, M naught, the given 0.9, M naught 0.9 or 1. It means into 1 into delta 0.952, 0.952, right? Z naught, we calculate Z naught is going to appear 21.21 into ln of D by R, distance to the person, space equilatory. It means 1 meter. So 1 meter means 100 centimeters. It means you will get nothing but this land value, right? D 100. It means ln of 1 meter, okay, but centimeter. So it means 100 by 1. I run this value. Okay, you will get 83.68 kilovolt per phase. It means this is the RMS value. But we need often RMS value, but we need often line value. We need often line value. So it means root 3 into VD. So it means root 3 into 83.68 you will get. So this value you will get 144.95. So this is your RMS value. That is your RMS value. Yeah, Abhiram, you correct now. Yeah. This is the voltage at which your corona starts in your transmission line. It means you can able to get your hissing noise and production of your ozone gas. So that starts with the voltage. Your line voltage is going to be greater than this one, but 144.95 volt. Then you are nothing but it's going to be nothing but your corona is going to be get start in your transmission line conductor. It means that is going to be a 144.95 kilovolt, right? So then that means that your corona effect is going to get starting in your transmission line. Okay. So next problem. So here remember I have taken with respect of here temperature is going to be remains constant. When the temperature is going to be remains constant, so remember we have calculated we are using. So but if the temperature is going to be varying, here air density factor. Here remember I given the air density factor delta. Delta is equal to 0.952. But that delta 0.952 is nothing if the temperature is going to remains constant. But your temperature varies means your delta is going to gets varies. So next problem we are going to take it when the temperature is going to gets varies at different temperature. Then how we are going to calculate your delta. Then how about your maximum voltage MV. So based on that we will solve one problem. Okay. Sir?
determine the critical disruptive voltage and the critical visual disruptive voltage for 3-phase 50 Hz 132 kilovolt line situated in a temperature of 30 degrees Celsius at a barometric pressure of 74 mg, 74 centimeters. Okay. Conductor diameter is 1.5 centimeter, while the equilateral spacing between the conductor is 2.7 meter. Surface irregularity factor is 0.9 and MV is equal to often 0.75. Okay, so we know the formula critical voltage VB. This is the color of here VB. Okay. In the formula we know that the resistance of here or del G naught M naught ln of V by R. Okay, V of or 1 plus 0.3 by square root of R into del ln of we are going to use. This is a formula which we are going to use it to calculate your critical disruptive voltage and critical visual disruptive voltage. Okay, so here I have to calculate the delta. So the delta estimate. So delta is equal to 3.23, 3.92 D by 273 plus 3. Into 74 divided by 273 plus 30. So you get delta 0.9573. Come on, give me the answer. So what is the G naught? But G naught is not mentioned in that one. Your G naught is not mentioned. So what we are going to do? What is the G naught? What is the G naught? It's your dielectric strength. So what is your dielectric strength? The dielectric strength of your air. That is going to your dielectric strength of air. It is not given. My PV will be equal to the value of 1.5. So it will be 1.5 divided by 2. So it will be 1.5 divided by 2 delta 0.997 into G naught. So 21.21 M naught regularity factor. M sorry, distance is 2.75. You will get BD. You will get what is your critical disruptive voltage. You will get what is your critical disruptive voltage. So that you have to find out in terms of your line. Here per phase, you will get per phase value. You have to convert to of your line voltage. How much you are getting? Nobody is there? Dinesh? Arinesh? Jahavar? Get me the answer. You will get 18.92 kilovolt line voltage. Unit of line voltage. Your answer 85. But this number can be upon line voltage. So this is your RMS value. This is your RMS value. Okay, I need upon line. So it means 80.3 into voltage. So you will get 1 kilovolt. So this is your destructive voltage of line voltage. Now we have to calculate your visual critical voltage MV 0.75. MV is 1.75. Delta value 0.97. 0.9573. 21.21 into R into 1 plus 0.3 by square root of 0.75 into delta 0.95. 0.9573. Okay, of 275 divided by 0.75. Get me? Get me what will be the value? multiply, you will get volts per phase is the maximum value. But I need a line value. It might be equal to 91.1 kilovolt into root 3. I will get 158.15 kilovolt. This is my corona starts to occur at voltage of 145. Violet glow. You can able to get your hissing night and protection of ozone gas at the value of 145. Means your corona start occurring on your transmission line, right? But the visual, it means but your blue, violet glow will be seen at the voltage of 150.15. It means you can able to see your violet glow, okay, at the voltage of 158.15. At the voltage of 158.15. It means you can able to see your violet glow. Okay. So you need to remember these two formulas. You need to remember this formula for visual critical distributed voltage and visual critical distributed voltage. Formula you have to remember to solve the problems on your corona. Okay. So you can calculate your power losses also. You can able to calculate your power losses. If you know your voltage, then you can apply the formula for your power loss formula. Then you can able to solve your power loss on your corona. Okay. Any doubt? Students, so that's all with your module 2. Module 2. Okay. So module 2, the first topic what we see is the parameter of transmission line. We have seen the parameter of our transmission line. Okay. So it means how to calculate the resistance, inductance of the transmission line, capacitance of the transmission line for various circuits, either single circuits or double circuits. How to calculate the inductance of our transmission line. Then we have seen the capacitance of our transmission line. How to calculate the capacitance of our transmission line. Okay. So this is the first half of your module 2. With that, we have seen the various effects of our transmission line. Skin effect, proximity effect, corona effect, and your Ferranti effect. Okay. So next part of your syllabus we see is the performance of our transmission line. Performance of our overhead transmission line. So for performance analysis, we have categorized the transmission line based on the voltage and distance as often short transmission line, medium transmission line, and long transmission line. So we did the mathematical modeling for a short, medium, and long transmission line. So we can able to analyze the using that model. We can able to analyze the performance of our short, medium, and long transmission line. Okay, so but we have seen how to calculate the sag and tension in our overhead transmission. What is the often sag? How to calculate the sag and tension in our overhead transmission line, and we have seen the different types of towers in our transmission line. So that's all with your module 2. Okay, that's all with your module 2. Okay, so already I have posted the material in the Google Classroom. I have posted the material in our Google Classroom. Okay, you can download the material, study material. You can download your study material. Okay, from the Google Classroom. So in the Google Classroom, you'll have the notes. Okay, you'll have the notes also, right? And you'll have the book material. Book material also I have uploaded in the Google Classroom. Okay, you can go through that one. So prepare. So any doubt? So if you don't have the doubts, we'll wind up this session. If you don't have any doubts, we'll wind up this session. Okay.